Now let's look at this. The first term we have. What is it? V is a scalar function, right? V is like our g here, right? So V is like our g here. So let's actually put terms by terms. So V is like our g here. How about this? This is actually the divergence. Oh, it's not a very good line. So this is actually the divergence of what? It's the divergence of a vector field that's composed of du dx and du dy, right? So it's the divergence of the gradient of u. Because the gradient of u is partial x, partial y, right? So now we have this term, the gradient of u is now corresponding to our h. And this can be written as the boundary term minus this. So the integration by parts goes as follows. Let's go back to our light blue line. It is equal to minus, let's write down the volume integral first. We have h, which is the gradient of u, right? So that's the vector, dot with the gradient of the scalar v. So dot with gradient of v, right? dx. So that's the volume term. And the boundary term, we have the normal dot with gh, and g is our scalar v, and satisfies the boundary condition v equal to 0 at the boundary. So that is gone, right? So we don't have a boundary term. So we can just keep writing the leftover term, integration of v f equal to 0. So the weak form is really this equal to this, right? Get rid of the minus sign. So the weak form is gradient of u dot with gradient of v dx equal to integration of vf. So we have derived our weak form of an equation in 2D. And compare that, if you remember for a moment, our one-dimensional weak form, right? Integration of 0 to 1, partial u, partial x, partial v, partial x, dx, equal to integration from 1 to 0, 0 to 1, v times f dx, right? I mean, it's exactly, it's very good analogy, except for you think of ddx is like the gradient in one dimensions. Okay, and the multiplication is the dot product in one dimension. Okay, right. So now let's discuss how do we apply finite volume. Up to now, we derived the weak form and everything is exact and precise, right? And this weak form has to hold for any v that satisfies the boundary condition and being differentiable. So again, in two-dimensional, we restrict both our solution u and the test function v into a class of functions, into a restricted class of functions. And the easiest or most elementary form of finite volume, which is already very useful for equations like this, is exactly the same kind of class of functions as we discussed in one dimensions. It is, again, piecewise linear and continuous. Okay, so how does that work? First of all, this class of piecewise linear and continuous functions works best if you have simplex elements. A simplex elements means triangles in 2D and tetrahedrals in 3D. So how does a piecewise linear and a continuous function look like? So let me just draw an example of a contour line. What if I just pick a node and say, okay, the value of this of my function at this node is equal to 1, and the value at all the other nodes are equal to 0. Note that this is actually a nodal basis function, right? It's the same as what we had in 1D, like the head functions. We force the function to be 1 at one grid point and 0 at all the other grid points, and what we get is like a head basis function that's piecewise linear and also continuous. In this case, let me draw a contour line of this function, right? The contour line in all of these elements are actually trivial because everything is 0, right? So if I know the function is 0 here, 0 here, 0 here, the fact that it has to be linear basically forces the entire function to be 0 on these elements, same as these elements. So on every element that are surrounded by 3 0 nodes, the value of the function is actually exactly 0. The only part that the function is non-trivial is around the elements, right? Is in the elements around this one node. Now let's draw what the function looks like in this element. Here the value has to be 1 and the function has to be linear, which means the contour lines has to be like that, right? Okay, it's equal to 1 here, and it is actually a constant linear slope. It's like one side of a pyramid, if you think about it, right? And along here, it's the same, right? It's basically another side of this pyramid, except for this pyramid is not having 4 sides. It's not a 4-sided pyramid. It's 1, 2, 3, 4, 5, 6. It's a 6-sided pyramid. And if I draw the contour lines carefully, the contour lines look like that. Okay, yeah. So, well, didn't do it very well. The contour lines look like something like this. So basically, you can imagine I have a pinnacle here, and the base of the pyramid is the size of the triangles around this point, and I have a pyramid on which side each side of the pyramid is exactly linear. This is actually one basis function, right? So I can construct different basis functions, each one having a value of 1 on every different node. So again, I'm going to be representing my U as a summation of the k's, where k are all the interior nodes of uk times phi k, where each phi k is such a head function. Okay, and I will choose my v to being v1 or v2, etc. Basically, again, each times one of these head functions. Okay, then I plug this u into this weak form, and I plug these v's also into the weak form. I have, again, n unknowns, n equations. I mean, the only difference is now I have to be able to integrate the gradient of one of these basis functions times the gradient of, let's say, another basis function, and be able to compute is the integral of the product of the pairs of gradients. As long as I can do this, I can substitute these pre-calculated integrals into my matrix, assemble them into a matrix, and solve and get the solution of the finite element. All right, so this is really how we do finite element in 2D and also similarly in 3 dimensions, except for the elements are no longer triangles but tetrahedrals, and you can build this kind of a 4-dimensional pyramids and use these as my basis functions. All right, this is what we're going to be discussing on 2 and 3-dimensional PDEs. And any questions you have, I can stay here for a few moments to answer this. Thank you.